Hello, I'm Seema and welcome to part 3 of the videos titled Electronic Configuration of Atoms. In the first two videos, we did the electronic configuration of the first 20 elements. In the video number 1, I did the first 10 elements. In the second video, I did the configuration of the next 10 elements, that is from sodium to calcium. And now we are going to do the electronic configurations of the next 10 elements, that is from scandium to zinc. Let us move on with it. As the electronic configurations, as we move on in the periodic table, following the Pauli exclusion principle, the Hund's rule of maximum multiplicity and the Aufbau's principle, we sometimes find that there is an exception to the rule, and there are reasons for these exceptions for the rule, and these exceptions become visible in these 10 elements now. So let us start with them. We have now filled 20 electrons of the element before it, which was calcium. Calcium had atomic number 20, and the electronic configuration of calcium was 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2. Now the 4s orbital is completed, and the next orbital after the 4s is the 3d orbital. So the next orbital that has to be filled up is the 3d. We know the 3d subshell has 5 orbitals and each orbital can have 2 electrons. So the next 10 electrons logically should be going into the d orbitals. And that's the reason why in the periodic table these elements, they form the first transition series and they form the d block elements. These are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These form the first transition or the d block elements. There are 10 rows of elements in which the d orbitals are being filled up. So let's start with scandium. Scandium has 21 electrons. Now up to calcium, the electronic configuration has already been filled up. So calcium would be, now we'd go to neon, okay? Neon was only up to here, and argon is 18. So we'll go up to argon. For scandium, I'll use the core of argon. Now what does that mean? Argon was the 18th element, and the configuration would be 1s2, 2s2, 2p6, that makes it 10 electrons, 3s2 and 3p6. If I write argon in bracket, it means these 18 electrons are already filled up, and now I move on to the next one. So the next is 4s orbital. It has 2 electrons in the 4s orbital and 3d orbital. You know, when we are writing the electronic configurations, although the 3d orbitals fill up after 4s orbitals, yet we write the 3d orbitals first because that is the third shell. And the 4s is actually the 4th shell, so we'll write it later, although it has filled up first. So we'll write now 3d would be 1 and 4s is 2. Am I clear? So what has happened now in scandium? 1 electron moves to the 3d orbital. Then, according to Hund's rule of maximum multiplicity, what would we expect? We would expect these 3d orbitals to be singly occupied first. So the next, let me do the next two and then I'll explain something. Titanium now has 22 electrons, therefore the next electron, the 22nd electron, goes to the second 3d orbital. So it would have configuration argon, 3d 2, 4s 2. Now vanadium would be argon, 3d 3 and 4s 2 because 1 electron moves here. Now in chromium, we find that chromium shows an exception to the rule. It does not follow this sequence strictly. And what is the difference that we see in chromium, or what is the configuration? Chromium has 24 electrons. Now we have solved 23 electrons are already here, as in the case of vanadium. So what happens in the case of chromium? 1 electron should go to 3d orbital here logically, yeah, because that is what we've understood. But we find that 1 electron does go to the 3d orbital. At the same time, 1 electron of the s orbital, instead of staying here, it moves from here and it jumps to the previous shell. It moves and comes in and jumps here. One of the electrons of the 4s orbital jumps into the 3d orbital. So this is an abnormal configuration. It is not what we would expect according to the three rules that we had been following. The Aufbau's principle, the Pauli exclusion principle, and the Pauli exclusion is applicable all the time, and the Hund's rule. Now what is the reason for this electron to jump into the 3D and make 4s orbital half occupied or singly occupied? Let me first write the configuration, then I'll explain to you. This would be argon, and here we would expect it to be 3d4 and 4s2, but it becomes 3d5 and 4s1. The reason for this, there are three reasons. One, we know that electrons repel each other. We are aware that electrons repel each other, and if there are degenerate orbitals, they always try to occupy the orbitals singly first, and then the pairing starts. In the case of the 3d and the 4s shells or the orbitals, the difference between the energy of the 4s and the 3d orbitals is not very large. It's very little. Therefore, it is possible for an electron to jump from 4s orbital to the 3d orbital, which actually is of higher energy. It is possible for it to. Now you can imagine there is one swing in the park that is separate, and there are 5 swings in a row. On the one swing there are 2 kids who are playing, and the 5 swings are a little far, so the kids have to run a little more. But when the friends come, they run to the 5 swings because there are 5 swings, and each one of them, 4 kids, they occupy 1 swing each. So these 2 kids who are on one swing, they feel that one of the swings is empty there. If one of them just makes a little effort, he can jump and occupy an empty swing. I simplify it a lot with a swing, but actually it's somewhat like that, you know. The electrons, they repel each other and they try to singly occupy the orbitals. That is one reason that electrons repel. The second reason is that when these electrons, whenever these orbitals or the subshells are half filled or completely filled, they acquire extra stability. They are more stable. Half filled and completely filled subshells are always more stable. So, in order to make it half filled, the 3D subshell should have 5 electrons, 1 in each of the orbitals. And in order to do that, 4s was completely filled, but it was only 1 orbital. And 3D are 5 orbitals. Just by disturbing one of the electrons in 4s, it is possible to acquire half-filled orbitals, half-filled subshell of 3D, and 4s automatically becomes half-filled. So, although it is not as stable as completely filled, but it is somewhat stable. Therefore, the electron chooses to jump into the 3D orbital. So, that was the second reason. The third reason is that whenever electrons occupy the different orbitals, degenerate orbitals singly, this is the quantum mechanical model. Electrons are not fixed. When we say that the electron is present in this orbit or orbital, we call it the probability picture. It may be present there. Psi square, if you remember, only tells you the probability of finding an electron in that orbital. So these electrons, they are not fixed to that orbital. What they do, they exchange their positions. They just flip their positions. They're naughty, like kids in the park. So they keep changing the swings. And when they change their orbitals, they release some energy. And this energy is known as exchange energy. The energy is known as exchange energy. And if you have, let us say, 5 orbitals, then out of 1, 2, 3, 4. So 1 electron, 2 electron. Only 1 exchange is possible. But if you have 3 electrons, then this exchange is possible, and this exchange is possible, and these 2 can also exchange with each other. If you have 4 electrons, the number of exchanges increases. Now this exchanges, this exchanges, this exchanges, then this exchanges with this, and this exchanges with this. So number of exchanges increases. So the exchange energy also increases. And if you have 5 of them, the number of exchanges is still more. here, 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 and here. So the greater the number of degenerate orbitals that are singly occupied, more will be the exchange energy. And that also is the reason why half-filled subshells are more stable. And that is why we find some abnormal configurations. And that one example is chromium. So we usually, in your book, you'll usually find a star in its configuration. That this is an abnormal configuration, an asterisk over it. Then comes manganese. Manganese is 25 as expected. This is argon. 3D already has 4 electrons. The 5th electron would go into this. And 4s is again 3d5, 4s2. Right? Iron now would be argon. 3d5, sorry, 3d6. Now the next electron of iron, the 26th electron, would go to the pairing in 3D will start, so it will be 3d6 and 4s is 2. Cobalt now is argon, 3d7, 4s 2. The next electron here pairs. And nickel, as expected, the next electron would go here. So the 28th electron would be argon, 3d8, 4s